Now we're going to talk about collections of sets, and things are going to get a little bit more abstract. And we'll try to have some concrete examples, and I'll try to give you some help as to how to think about it as concretely as possible. But measure theory is very abstract in nature by the time you get to looking at these sigma-algebras and Borel sets and things that we're going to be looking at. So we'll do the best we can to see as many specific examples as we can, but you will have to work a bit, I think, at getting the levels of abstraction working, because we're going to be dealing with sets, and we're going to be dealing with elements of sets, of course, but we're also going to be dealing with subsets of sets. We're going to be dealing with sets of subsets of sets, which we'll call collections of subsets of a set, but that just means they're going to be sets of subsets of a set. We're going to be sometimes dealing with lots of collections. We're going to have a family of collections. Sometimes we need to look at lots of different collections of sets. By the time you're doing that, you're working at quite a high level of abstraction. And the amazing thing is that the proofs are really easy, but the level of abstraction makes it hard. I'm not saying all the proofs are easy, but you get to by going for more abstraction, you get much shorter proofs, but you do have to work with the different levels of abstraction. Okay, so I'm going to talk about general sets X, but you may well find it easiest to imagine that X is really the real line, or at least a metric space. But a lot of what I'm going to say will work in any set X. Some of it will work in any topological space. So most of what I'm going to say will be pretty general, but if you want to keep it concrete in your mind, you can think about the case of the real line, or maybe r squared, r cubed if you want to, because when we deal with measure, we're going to be talking about things like length, area, and volume, different ways of measuring the size of sets. And so most of the time, then, in our applications, maybe we're going to be thinking about the real line, or r squared, or r cubed, when we come to what's called Lebesgue measure. So as I just said, we're going to be looking at collections of subsets of a set. Sometimes we might talk about families of sets or collections of sets, or we might have a family of collections of sets. There are all sorts of things like that we might use, but I'm not going to have anything that isn't a set here. So if I say a collection of sets, that just means a set of sets. And if I say a family of collections of sets, that's just a set of sets of sets. I mean, that's bad enough, but I'm not dealing with anything that isn't a set here. So, what's our examples and our notation? We take some set and we want to know what's the largest possible collection of subsets of X. And that's the power set of X, P of X. I can't do that particular P. I normally write this curly P, means the same thing. So if I write it, I'll have a curly P. You can write 2 to the X if you want, that's fine. That's another notation for the power set. And that's the biggest possible collection of subsets of X. If it's a finite set, the number of elements in the power set is 2 to the power of the number of elements in the set. So that's where this notation comes from. But if the set's infinite, then there's an awful lot of subsets. There are always more subsets of the set than there are elements of the set. That's our theorem, which we won't go into. So whenever you've got an infinite set, and you look at the power set, a set of all subsets of it, that set is always bigger, strictly bigger cardinality than the set you started with. Now, we can always take no subsets at all to form the empty collection of sets. It's not very interesting, but there is an empty collection of sets. We won't usually work with it. We usually want at least one set in the collection, and we'll usually insist that at least the empty set is in the collection. Now, this does cause confusion, because what is the difference between the empty set and the set which has got the empty set in it and nothing else? Answer: the empty set has no elements, And this thing C1 has got one element. And the one element in C1 is the empty set. The empty set, being a thing, is a perfectly good thing you can put inside a set. So this is different from, so this is not the empty set, this is the set which has got the empty set in it. It's got one element. And then here's another one that we will come across sometime, which has got two elements in it, usually. Why do I say usually? Because if X is the empty set, which it could be, then there's only one element in it, in that set, so it's the same. But that's why I said usually, but we won't usually work with the empty set X, so that particular collection C2 there, and this is temporary notation, C1 and C2, it's not going to be, I'm not going to be using that notation all the way through, but I will mention those collections occasionally. So let's have a look at what sort of collections we're going to be dealing with. Well, first of all, let me remind you that you already know about certain kinds of collections of sets, in case you'd forgotten. You've already seen the notion of a topology. That's a kind of collection of sets. So here's another way of saying you've got a collection of subsets. If I write tau as a subset of P of X, that means, well, P of X is the set of all subsets of X. Tau as a subset of that means tau's got some or all of the subsets of X in it. So that means, that's another way of saying tau is a collection of subsets of X. And then you need, first of all, you need that the empty set and X are in tau. Secondly, tau is closed under finite intersections. So U and V in tau implies U intersection V is in tau, etc. Once you've got two, you can get finite intersections. Okay, and thirdly, you need arbitrary unions. This is for topology, right? So this is for tau to be a topology. So it's tau, it's closed under arbitrary union. That means you can take as many, even uncountably many, open sets, and the union has to still be open. You can take the set of closed sets as well. So if X tau is a topological space, consider, let's call it curly C for a collection. That's a curly C there. To be E contained in X such that E complement is in tau, noting that E complement is X take away E. That's a set of closed sets. That's a collection of all closed sets. Then you get different properties. Well, some different properties. The empty set and X are still in C. That's okay. So we know what happens for open sets. What happens for closed sets with unions and intersections?
Closed under arbitrary intersections.
Arbitrary intersection and finite unions. Okay, so this time C closed. It's unfortunate that word closed. It's not the same kind of closed. Closed under an operation means that if you do that operation, you stay in the same collection. So that's closed under an operation. That's not the same as closed in a topological space sense. So it's unfortunate that when you talk about topological spaces and you say closed under, you have to remember that it's the other kind of closed. Closed under, so you get finite union. So E and F in C implies E union F is in C, etc. Again, once you've got unions of 2, you can get the finite unions from that. And 3. C is closed under arbitrary intersection. So you can intersect as many, even uncountably many, closed sets as you like, and it'll still be closed. So that's the collection of open sets, the collection of closed sets, and they've got certain properties. But we need to look at some different kinds of collections. For measure theory, you only really want to work with countable operations, not with uncountable operations, because for one reason, we want, for example, you want to say that points have got, suppose you're working in R squared, you want to say points have got area 0. Now, every set is a union of points. You don't want to say that we can add up all those zeros and get 0. But it's still true that if you do, there is a notion of adding as many zeros as you like to get 0, even uncountably many. But we don't want to allow that. We only want to allow countable operations. So when we deal with area, length, volume, you want the, we're going to want the measure of a countable set to still be 0, because we want to be able to add countably many zeros together to get 0. But you mustn't allow uncountable unions, or you're going to get everything, and then you want everything to have measure 0, and it's got very boring, which is not what we want. So we're interested in measure theory in countable operations, when you want to measure the size of the sets, and so on. So we're not going to have these arbitrary intersections or arbitrary unions when it comes to measure theory. But we will get other stuff that you don't have in a topology. So let's see what a sigma-algebra is. Well, there's lots of different ways to define it. I'm going to give you a very efficient definition, but then tell you the other properties they have, because the alternative is to tell you all the properties they have, but then it gets harder to check whether something is a sigma algebra or not. If at any point I accidentally say sigma field, that's because I grew up calling these things sigma fields. That's how I learned it in Cambridge, and I tend to keep reverting and calling them sigma fields accidentally. But most people in the literature call them something else, like sigma algebra or Borel algebra or something like that. If I accidentally use the wrong term, I'm still talking about the same thing, whether I say sigma field, sigma algebra, or Borel algebra. But I shall try to say sigma algebra. So again, we're going to use this notation. Let's get my red pen. Again, we're using notation A complement for the complement of the set, and we're working in some set X, so we'll know which set we're taking the complement in. That just saves a bit of writing. It's not essential, but when you come to doing De Morgan's laws and so on, it can help to just not to have to keep writing X / all the time. Too much trouble. So here are the three sigma field algebras that we're going to work with. We insist, well, so we're working with a set X and some collection of subsets, and we're going to say what it means to be a sigma-algebra of subsets on X, or sigma-algebra of subsets of X. But that takes too long to say and write all the time, so I abbreviate that to sigma-algebra on X, and I'm going to be calling it sigma-algebra on X throughout. It's like a topology on X, okay? But it means a collection of subsets of X. The empty set has got to be in the collection. You may wonder why I don't say that the whole space has to be in the collection. That's going to follow in a moment. So it is true that X has to be in the collection as well, but you don't have to check it if you've checked these other axioms. It's redundant, because I'm insisting that you can take complements. So closed under complement. Anything that's in, you can take the complement. So in particular, you can take the complement of the empty set, and you get that the whole of X has to be in. And then I'll insist that you're closed under countable unions. This is what I call countable unions, really countably infinite union, because finite sets are countable as well for us. Don't forget that our countable sets include finite sets, and even the empty set counts as a countable set. But so I use the term countably infinite if I want to make sure that my set is actually infinite and countable. And this is what I call a countable union. So I'm going to call this closed under countable unions. Or closed under countable union. So that operation of taking a countable union of sets in the collection, you can't leave your collection. That's what you need for a sigma field. Now that's already enough to make it a sigma field, but it doesn't make it completely obvious just how good they are. So let me just note that from S1 and S2, gives that the complement of the empty set is equal to X has to be in F as well. And some people throw that in. In fact, some people say that instead of saying the empty set is in, say that X is in. It's up to you which one you find easier to check when you're trying to check a specific example. Then what about unions of finitely many? We know you can take a union of infinitely many sets, a countable sequence of sets. So suppose someone gives you two sets, or finitely many sets. How do you show that the union of those, and they're in the collection, how do you show they're in the collection? So if you're given A1, A2, up to AN in F, how do you prove that that finite union is in? Because you only know at the moment that you can throw in a union of an infinite sequence. So how do you get a union of a finite sequence?
Take infinitely many copies of AN and then take a union with that, so you have an infinite union where...
Yeah, you can either repeat any of these sets infinitely often, or you can throw the empty set. That's another way of doing it. So, so there's two ways to do it. Either repeat AN infinitely often, for example, and that doesn't change the union. Or you can throw in infinitely many copies of the empty set. how do you get intersections? Suppose you've got A and B in F. How do you show that A intersection B is still in? Bit of De Morgan needed here. So A intersection B is the complement of something. What's it the complement of?
A complement, union B complement.
Yeah. Now, we know we've got A and B are in, so A complement to B complement are in. So A complement union B complement is in, by what we just did about finite unions. And then you take the complement, and that's in as well. So that's by above. By above and S1 several times. Okay? Complements of unions. And you do infinite intersections the same way. You want to know what the intersection is. It's the complement of the union of the complements. I got that right. The complement of the union of the complements gives you the intersection of the set. That's it. And that's by S1 and S3. Wait a minute, S1, S2 and S1. Which one is it? Sorry, did I use S1? I should have been using S2, shouldn't I? So S1 is a boring one. That was S2, and this is S2 and S3. Oh, what about set difference? What's another way of writing A take away B is a set difference?
A intersection B complement.
That's the one. So again, that's by above and S2. Finite intersection, and so on. So in fact, although I've given you a very small number of axioms for a sigma field, the actual conclusion is that sigma fields have got a lot of properties. Now, you need some examples. And I'll just start by saying that because we're dealing with countable operations here, but we've got complements, that means that most topologies are not sigma fields, they're sigma algebras, and most sigma algebras are not topologies, with some exceptions. And of course, the smallest ones and the biggest ones are okay. So these are what you call the indiscrete topology. That's the smallest possible one. That's also a sigma field, sigma algebra, if I can just remember to call them those. And the discrete topology is P of X, is also a sigma algebra. you can check those as a very easy exercise. I mean, the main thing is that if you've got a collection of subsets of X, then any union of subsets of X is still a subset of X. So you can't escape from being a subset of X by doing any sort of set operations working in X. And the other one, this one, the indiscrete topology is very easy special case check. There's not very much to check because there aren't very many sets available to work with. Okay, we'll stop there for today. Next time we'll be doing the Borel sets and sigma-algebras generated by other collections.